again. We are starting a new video related to artificial intelligence in the first part of the course and the videos. And in this video, I will look at the simple problem, which is a route planning problem. Now, how do we resolve a route planning problem? The main things what we have to consider here is basically the general route planning model. What is the model that we are going to use and what are its different components? First of all, we have the computational model that does the calculations. The second element, we have the routing algorithm, which is finding out the best route from one place to another. We have the practical application of the route planning. How are we practically going to apply it? Which information are we going to use? And finally, we have to prove that the algorithm we are using, that it is a valid algorithm. And this is a very important element in intelligence, artificial intelligence, and algorithm studies. But before we continue, don't forget to click on the subscribe button, click on the bell button, and every time we have a new video, YouTube will inform you about it. So let's start with the general route planning model. Here we see the model, we have the theory, the model, the algorithm, and the application. And we see that all these elements are in fact important. When we look at the supporting theory related to the used algorithms, that's a main part of this route planning model. There is a computational model that is based on graphs. The algorithm is there to find the shortest route, and the application itself is applying everything, all the measurements, all the calculations on a relevant selection of the map. We don't want to use the entire map because that would mean that we have too much information. The calculation time would be too long and a lot of irrelevant information would be in the memory. So these are very practical considerations when we are applying the route planning on a real model, on a real route that we want to travel. Let's first have a look at the model. The model is based on computational modeling based on graphs which have nodes and edges. The distance between the points is fixed, but the time can vary, and we can see that sometimes when we are looking at the route, we can say we want to have the shortest distance, or we want to have the fastest route completion. So these are two elements that we can consider. Graph problems are important. Here we are using graph theory, and there are a number of algorithms that support this. When we look at the graph, there are nodes and edges, basically the points and the lines or the roads between them. And when we look at the different edges, the distance between them is typically constant. In most cases, when we look at the route planning, the distance between the two places, according to some edges, will be always the same distance. When we look at travel time, like I said before, we can consider the shortest route or the fastest route. There are different applications. When you look at the navigation system, you can also select routes without paying for the route, for the highways, highway tax and things like that. So there are different elements that can be added to the model. The algorithm is very important because it's an algorithm which is looking at the shortest path, and there are algorithms like Dijkstra and Bellman-Ford which can assist you with that. So the algorithm is very important in AI in general, but also in routing problems. There are different algorithms that we can consider. I gave here two examples, Dijkstra and Bellman-Ford, but we will see that there are other algorithms that we can use. And when we will look at that, I don't remember in which part of these sessions, but we will see that we will also improve the efficiency of the algorithm by adding heuristics. Heuristics will help us to make a more efficient model, reduce the number of calculations, certainly reducing repetitive calculations, which can be a problem when we are considering certain algorithms. The next part is the application itself. Here we look at the relevant part of the map. So normally when we have the map stored, we have all the maps, and the maps that are available may be a lot larger than the part that we need. And you can compare this when you're going on a trip yourself. You are basically preparing the map. You have the map, but you will only take the relevant map. You will not take the map for all Europe when you want to travel within a country. When you're traveling between countries, you may use different parts of the maps. When we look at the application level, here we see again what I said before, that we will only look at the relevant part of the map, the part that we need for the route, and this will in fact help the performance. It will optimize the performance. We can really concentrate on what really matters. The last element is about the theory. We have to prove that what we are doing is working, and that we find a solution, and that this solution is preferably the optimal solution. When we look at algorithms, a very important element when we consider them is that we have to prove the algorithm before we can apply the algorithm. And this is a critical part, because we want to know that the algorithm will always be providing the same result when we do the calculations. Of course, certain conditions may change when we apply the algorithm, which may lead to some changes, but these are logical changes. Now, when we look at the algorithm, the theory, we have to understand how is the algorithm working, and we have to prove that it provides that same result, like I said, and it's of key importance that the result is repetitive. It's always the same, that we don't that the algorithm always ends out in the place where we want, giving the same result. When we look at algorithms, when we would go to that part in IT studies, you will see that there is a lot of work done related to proving algorithms. It's a very part of the education, and people who are defining algorithms, they will have to understand that the algorithm has a certain way of operating, a certain way of dealing with the data, and we have to prove that this is in fact always correct. So let's have a look at the summary here. We have the final model, we have the theory where we prove that everything works. We have the computational model where we use graphs with nodes and edges. And when we look at the distance here, the distance is fixed, but time can change. I look at circumstances on the road where we have some traffic works or some other elements that may lead to a different time. So we can select the shortest route, the fastest route, the route not using, for example, roads where you have to pay for passing through the roads, like for example in Czech Republic. When you drive on the highways, there are parts where you have to pay a highway tax, and you can tell or ask the model to find a route without using these roads. We have an algorithm where we have an algorithm where we are in fact solving shortest path questions. There are different algorithms that we use, and we can also improve the performance of the algorithm when we would add some heuristics. The final part is the application, where we reduce the problem by selecting only the relevant part of the map. So we're improving the possibilities that we can use, that we do the calculations on, which will lead to lower usage of memory, and of course the calculations will be a lot faster, and it's clear to understand that we want to have fast calculations, relevant calculations, because we're driving on the road and we want to have the optimal or the correct information in time. So that was it for this part about the simple road planning algorithm. Before we continue, don't forget to click on the subscribe button, click on the bell button, and every time we have a new video, YouTube will inform you about it. That was it for this video. I thank you for your attention, and I'm looking forward to seeing you in our next videos. Thank you, and bye-bye.